System level power estimation of SSDs under real workload using emulation. The abstraction as the performance of the solid state drives SSDs increases, the importance of the system level power estimation is always increased. In this paper, we propose a system level power estimation methodology for SSD design that uses silicon unmeasured power of each command. We use emulation to qualify the hardware along with the software under real workload. Experimental results show average and peak power was estimated with the maximum error of 8%. Introduction. Due to the faster and data transfer speed requirement, the performance of the solid state drives SSDs is constantly increasing. SSDs now support the PCI 5.0 interface with the sequential read speed. I read at a speed of up to 30,000 megabytes per second, and the higher performance often results in large power consumption, which is why the accurate power estimation is important. Figure 1 shows the component of the SSD. An SSD consists of the controller, SoC, the memory, storage, NAND, and a cache DRAM component. For the controller, we are able to use a mature SoC power estimation methodology, but the power consumption of the other components are hard to estimation. There had been a previous attempt to estimate the power of the memory subsystem. G et al. And used an equation-based method to estimate NAND or DRAM power. Using the power models, they were able to estimate the average power values. However, this method does not consider how power fluctuation aids during a command and is not able to estimate the power at a certain time. Therefore, they cannot estimate the peak power. Peak power consumption estimation of a device is also important, since the instantiated current consumption should not pass the PMIC's max input current. In this paper, we introduce our SSD system power estimation methodology. Estimating power of the realistic I/O operation using scenarios requires a verification methodology that can handle the large design of the SSD controllers, which is usually over tens of millions of instances and support the firmware. Simulation time needs to be relatively long, 100 milliseconds, as a 100 milliseconds, as a peak power usually occurs only when corner cases. We use an emulation-based hardware-software co-verification method to satisfy the hardware and software requirement. Figure 2 shows our UVM-based verification environment, which is accelerated using hardware emulator, similar to the method presented by Jane et al. For memory subsystems, we use internal status register of this emulator behavior models to analyze which command each component is running. We use real silicon requirements of each command to convert to the command information to power values. This allows concurrent estimation of each component power and thus the average of peak power consumption of SSDs. So we compare the SSD power estimation result with the silicon measurement. Figure 1 is component of SSD. Figure 2 is a verification environment. Figure 3, overview of SSD system level power estimation methodology. The SSD system level power estimation. In this section, we describe in detail how we perform a power estimation and how we obtain the required input for power estimation, especially the DRAM and NAND command loads. And figure 3 is an overview of our SSD system level power estimation methodology. We estimate SSD system power by estimating the power of each component, NAND, DRAM, and controller. We learn a real state usage scenario simulations by utilizing the hardware emulator. The A, NAND power. For NAND power estimation, we modified the behavior model and created an internal status register that represents for the command status. The active command we consider read and program and erase and read DMA and write DMA, and we also output if the NAND is the single level cell SLC mode or a triple level cell TLC mode. We created a status bits that represent the multiplane operation. Also, we created a dump file for each NAND channel status register. Figure 4a is an example of a one-channel two-way NAND configuration. The command dump log has timestamp and the command status of each way. We measure the input power value for each NAND command while considering SLC and TLC mode and multiplane operation. To increase the accuracy of our simulation, we set the AC timing parameters of the behavior model to the parameters measures alongside the power, so that the simulated SSD and read-write performance will match the measured performance. We applied the measures NAND command power when each command occurs to estimate the power of each NAND channel and accumulating the values to obtain the NAND power. The figure 4, NAND operation of one-channel way, two-way configuration of NAND command dump log. B. DRAM power. For estimating DRAM power, we modified the emulator DDR4 emulator model 4 model. Although the model is mostly encrypted, monitoring signals are provided in a non-scripted module to help analyze the DDR4 traffic. We used the command condition flags, which activated when a corresponding command is detected. To create the DRAM command dump log by detecting precharge, active and writing and read command, we disabled the condition flag for the refresh command. The rapid occurrence of the command increases the size of the dump file, which makes it a probability when the running multi-millisecond simulations. Power calculation is similar to the method presented in the DRAM power. We use the command dump log and the measures IDD current values to calculate the power of each command. Refresh power calculation uses the average refresh interval and R reference I and the refresh cycle time and RT, RFC and from the JEDEC DDR4 standard and burst refresh current IDD for IDD5B. The C is controller power. We estimate the controller power using the standard SSD power estimation flow. We obtain the SSD dump files and the input to the synopsis prime power and a gate level analysis power estimation tool to improve the correlation with the power measurement of a silicon chip. We set the process, temperature, and voltage conditions to be similar to nominal operating conditions. To analyze peak power situation, we would like to note that by approving the state of signals of a controller, we are able to track the controller operation in a peak power situation. We could also perform the power aware simulation by adding UPF files and tracking the isolation and retention power gating signals. This would allow us to check the state of each power domain during the simulation. However, for our usage cases, we only estimated the power of the maximum performance situation, which did not require considering power saving modes. D. SSD system power. Using the above NAND and DRAM and controller estimated power values, we estimated the SSD system power. We estimate the system power differently for systems and have an internal PMIC or a usually external PMIC. For a system with an external PMIC, we only need to estimate the sum of the current of each component. For a system with an internal PMIC, and we measure the PMIC efficiently for varying power current to create an efficiency graph similar to the one used by LG Salim and PP Mercier. We then convert the PMIC output current values to the obtained PMIC input current. The 3. Experimental result. We applied our system-level power estimation methodology to a commercial SSDs and compared the average, Table 1, and peak power, Table 2, the silicon chip measurement. The controller design size is on the scale of the tens of millions of instances. We used the Veloce hardware platform to perform our power estimation. However, since we do not use the vendor-specific feature, we can use other emulation platforms in a similar way. Also, for a smaller design, we can use Veloce simulations to obtain a power estimation result, since concept-wise our methodology does not require emulation. We normalized the estimated value their table to the measured power. Identical product formula was used during the silicon measurement and simulation so firmware operation differences does not cause the estimation errors. We cannot perform estimation on a similar time range to silicon chip measurement, as the silicon chip measurement were performed seconds range and estimations were performed for 10 to 100 milliseconds. Table 1, average power estimation result. Table 2, peak power estimation result. We estimated power of 4 I/O performance scenarios: sequential read and write and random read and write. For average power, the average error is 3%. The largest error is 5%. If we look at each component, the maximum error of the NAND was 9%, DRAM is 10%, and controller is 3%. SSD controller power estimation is measured as a periodic waveform, which occurs multiple times inside our estimation time range, which is why we were able to estimate the average power estimation accurately. The peak power estimation have an average error of 5%, and the largest error is 8%. One of the reasons we think the accuracy drops compared to the average power is due to cases where the peak power occurs in the core cases. If our simulation does not include the corner cases where the silicon chip measurement peak occurs, we would miss the peak power event. This would require specific test cases to recreate the peak power scenario, which verification engineers would be able to correct over time when validating similar designs. For summary, we propose a system-level power estimation methodology that uses the silicon measures compare our command power to estimate memory subsystem. We obtain the command info by modifying the memory behavior models. Emulation is used to accelerate the verification time. Results show that the average and peak power was estimated with the maximum error of 8%. Okay, references. Today I read this DVCON paper 2023 silicon system level power estimation of SSDs under real workloads using emulation. Thank you again, and see you next time.